Hi everyone, let's start lecture 5 or chapter 8 of our textbook, and it's about push and pull production control systems, or it's also called MRP, Material Requirement Planning, and JIT, or Just in Time. This chapter will be covered in two sections in 2 weeks. So section 1 is for this week, and this section will be covered in two pre-recorded videos, and this is part 1. So on the course map, we are in chapter 8, push and pull systems, MRP and just in time. And in the introduction part in this chapter, you'll see why this chapter is located here. I mean, right after chapter 3, aggregate planning, and also before chapter 9, which is operations scheduling. Okay. So as the agenda of this chapter, at first we'll have an introduction to MRP and just in time. So we'll see what's the definition of material requirement planning and just in time, and what are the concepts and how they can be applied in a manufacturing environment. And then we'll learn about the MRP basics, which includes a production plan, into independent demand versus dependent demand, and also what are the major inputs for MRP, material requirement planning. And at the end, at the end of this section, we'll have the explosion calculus, which are used to do the calculations in the process of MRP. And at the end, we'll have an example. Okay. So now let's have the introduction part first. I can say almost all the chapters that we have in this course are in the area of supply chain management, or SCM. So in supply chain management, one of the main activities is the actual production process, and the flow of goods and material in the production process will have significant impact on the quality and the quantity of the finished products. Okay, so there are two fundamentally different philosophies for managing the flow of material and sub-assembly parts and goods in a manufacturing environment, and they are push or MRP and pull or just in time, JIT. So these two philosophies are completely different. In pull system or just in time, the system reacts to a present demand. So here, system will produce if there is demand. But in the push system, system will have a forecast on the future demand, and then based on that, will produce. And then after production, system tries to sell the produced items. So this is called push, and the other one is pull. So I'll explain more in a figure in the next slide. So as you see here, we have two sides, suppliers and customers. So in the push or MRP system, the manufacturing environment, I mean the manufacturer will have a forecast on demand, and then based on that will supply the parts and material from the suppliers, and then will produce items, and then will push the departments, I mean the marketing and sales department, to sell the produced items. And then the marketing department will push customers by having promotion plans to to encourage them to buy the produced items. So this is called a push or MRP system. But in the pull system or just in time, at first we'll have requests from customers. So in this system, customers will have requests first, and then they will pull the manufacturer to produce their requested items. So here all the levels in the manufacturing and supplier will be based on request. So yeah, I mean, sales and marketing department will place order for production based on the customer's request, and then the production department will produce the items based on the request of marketing department. Then the supply part, I mean the supply department will supply material and parts from suppliers based on the request of the production department. So because of that, this is called pull system or just in time. Okay. Let's start the definition of MRP, material requirements planning, and JIT or just in time. So MRP is a process that we translate the aggregate plan of end items, I mean finished products, into the material and sub-assembly parts. So in chapter 3, after chapter 2 that we make the forecasts of future demand, and then in chapter 3 we'll learn how we can prepare aggregate plan for end items for finished product. Now we can use that aggregate plan as input in for MRP, and then in MRP process we will translate those plans for to the production of material and sub assemblies. Okay, so this is called MRP, and just in time is based on the Japanese Kanban system developed by Toyota. So the main goal of just in time is having a zero level inventory, or let's say absolute minimum. So we may not I mean reach to the zero level inventory, but we'll try to reduce the level of inventories in the work in process as much as possible. So this is called just in time. Okay. So just in time is a classic pull system. So in just in time, there will be production if there is demand. So first we need to have demand, and then based on that, the production process will be operated. So because of that, it's a demand-driven system, and also we do have small lot sizes here. So yeah, since we are not going to produce and keep the items in the warehouse in hope to have demand in future, that's not the case in just in time. So we are producing just based on the demand, actual demand. So we'll have small lot sizes here, and slow response to changes in product sales. Yeah, since we don't have inventory of produced items, so our response for large changes in demand will be slow than the push system, since we do have inventories, right? So if you want to compare MRP and just-in-time, the main advantage of MRP over just-in-time is working based on the forecast. So if it's going to be substantial variation in demand in future, and if we are able to forecast that variation, then we will be prepared for that, right? So but that's not going to be to happen in just in time. So this will be the main advantage of MRP over just in time, and the main advantage of just in time over MRP is reducing inventories to a minimum. So yeah, so but none of these two actually is complete enough in order to be applied in a company in a manufacturing environment. So maybe both approaches can be applied in such circumstances that we can utilize the benefits and advantages of both approaches at the same time in an organization. So the hierarchy of MRP, here we do have three phases, let's say. At first, we need to forecast the aggregate demand over T period planning horizon. So we can do this by the techniques that we have learned in chapter 2, and then determination of aggregate production level, workforce level and inventory level. So yeah, that's aggregate planning, and we learned this in chapter 3. And now we are going to convert or translate this aggregate plan into the production plan of materials and sub-assembly parts, and it will be based on weekly production schedule. So this is the case that we are going to learn in this chapter. Okay. So in the production plan, at first we prepare a master production schedule, or MPS. So MPS is a master production schedule for the end items, for the finished products over a period. So the data sources that we need to have in order to prepare an MPS will be firm customer orders. If we do have forecasts of future demands by item, I mean end items, and safety stock requirements, seasonal variations, and also internal orders from other parts of the organization. Okay, so yeah, these data will be used to prepare a master production schedule for the end item. And then by having that, we go through the material requirements planning, or MRP, and then we will translate those MPS into the components and the materials that will be used to produce the end items. Okay, and at the end we will have a job shop schedule that will be a schedule of the low-level operations, and we'll learn this in the next chapter. But this chapter is focusing on MRP. Okay. So in a production plan or production process, we'll have 3 phases. In phase 1, we will prepare a master production schedule, MPS, for end items. And then in phase 2, we will translate the MPS into the materials and components. So it's called MRP here. And then in phase 3, we will prepare the detailed operations schedule, and we will learn this in the next chapter. Okay. In MRP, we will have 2 types of demand: independent and dependent demand. Independent demand will be the demand of end items, the ones that we will forecast. So they are considered as independent demand, so for the finished end items and or for spare parts. Okay, and dependent demand will be for the material and components that will be used to produce the end item. So by having the demand of end item as independent, then the demand for the material and subcomponents will be a function of the predicted demand, right? So because of that, here we call the demand of material and subcomponents as dependent demand. Okay, so now we can say the purpose of MRP actually is to make sure that all materials and subcomponents and sub-assembly parts that we need to produce the end items are available in the right quantities at the proper time. So yeah, as you see here, any production plan will include the quantities, and it will be based on a schedule, right? So we need to have right quantities at the right time. So yeah, right quantities at the proper time, so that end products, I mean the independent demand item, can be made to meet the MPS. Okay. Now we will see what are the 3 principal inputs for MRP. So the MPS, the master production schedule, will be the first input for MRP. So by having MPS, we will have the independent demand of the end item, and then based on that we can calculate the dependent demands. Okay, and then the second input for MRP is called bill of materials, or BOM. So it will be a structure for the product showing that what are the sub-assemblies and components or material, and in what structure we need to assemble those parts and use those materials in order to make the end item. So based on this product structure, we will have the sub-assemblies, components, raw materials, and usage quantities, how many of those parts are needed for one end item, and also lead times in order to prepare or produce those sub components. Okay, and the third input here will be inventory status, or IS. So we need to know that how many items for each part or each material that we have on hand or on order. So yeah, here we'll have an inventory status record, ISR, and it will record the item number, description, lead time, and also a lot sizing rule. Okay. So the main calculation, or I can say process in MRP, is called explosion calculus. So in explosion calculus, we'll have a set of rules for converting MPS to MRP. So here we'll see how can we obtain the requirements. I mean, the quantity and the time, so it will be requirements schedule for all sub-assemblies, components, and raw materials that we need to have in order to make the end item. So here the key input will be the product structure, or bill of material, or BOM. So what do we mean by BOM, or product structure? Here we'll show all the components and sub-assemblies of an end item, like a chart with having hierarchy levels. So because of that, we can say there is a parent-child relationship between the components and end items at each level. So the top level will be the parent of the lower level items. Okay, so and then we will mention the number of periods required to produce each component, and also the number of components required at the child level to produce a unit in the parent level. So these are the data that we will include in the product structure. Okay. So here we have an example for product structure, or BOM. So we can show this by a diagram or indented structure, as you see here. So here the end item, our finished good, will be made by two sub-assemblies of A and B. Okay, and as you see here, the number that we do have in the bracket here mentions the units that we need to have of that item in order to produce the end item. So we need two sub-assembly of A and one sub-assembly of B in order to produce one unit of end item. And these are the lead time. So 1 week and 2 weeks will be the lead time of producing one unit of these parts. Okay, so in the lower level, as you see here, the sub-assembly A will be produced by subcomponents of or parts of C and D. Again, as you see here, we'll need 1 unit of C and 2 units of D in order to make 1 unit of A. And also we do have, again, the lead times here. Okay, and for B, as you see, we will use C as well. So as you see here, C is common in A and B. So we will need 2 units of C and 3 units of E in order to assemble the sub-assembly of B. Okay, and also we do have the lead times here. Okay, so yeah, this is called product structure diagram, or product structure, or bill of material, BOM, and this will be the key input for the explosion calculus, or the calculations that we will have in the MRP process. So in the next part, we'll see how can we do the explosion calculus, or the detailed calculations in MRP process, in order to obtain the dependent demand of sub-assembly and sub-component parts based on the demand of end item. Okay, thank you.